Let us start where we have ended in the last lecture. We have already plotted Pourbaix diagram for nickel, and that diagram like this. So it should connect here. So this is the diagram for, and this is coming at pH equal to 6 if the concentration of all the species, ionic species are 1, and this is Ni plus plus region, this is Ni, and this is NiOH whole 2 of NiO. We have seen that. Now we are left with the reaction which involves hydrogen ion, water and oxygen. We have already seen, and this is coming and touching at 0.11 volt, and this is minus 0.24 volt. It's not exactly according to the scale, but this would come like this. Now we have already seen, if this is my 0 volt, we have already seen the equation H plus E going to H2O. That case we have seen this can be related to E equal to minus 0.059 pH. So this can be again, this equation can be again plotted in this E versus pH diagram, which is nothing but from 0 it will start, because when it is 0 volt, that time the pH should be 0, because if you extend this relay equation, then it would come E equal to E0 minus 0.059 pH. This is nothing but RT by F. You just put that value 8.314 into 2.303. It would become, so this would become, if you take R equal to 8.314 into T, which is at 25 degrees Celsius, 298 Kelvin, and F is close to 96500 coulomb per gram equivalent, then you will see that this equal to this close to 0.059. Then there will be other parts also. So we are taking it as 0.059. So if pH is 0, then this would become E equal to E0 for this reaction, and already we know that E0 for hydrogen reaction is 0. So this value, pH value, should be 0. Now we have started with the next relation, next equation, which is H2O plus 2E going to H2 plus OH minus. This is another reduction process. So we have started calculating. Now we have already seen that this becomes, which is ox red, would be equal to E0 ox red minus, if you simplify it, then it would become 0.059. Now you can also use 1, or you can even omit this 1, because it's in 3 decimal part if you keep it. So then this is become OH minus. Now this same relation we have to find out what is the value of E0, and for the value of E0 would be equal to del G0 for this reaction with a minus sign, because del G0 equal to minus NFE0 and N is 2 here. So, this should be 2 N2 F, which is 1 Faraday. Now, this del 0 we can also find out, minus 2 of 147.1, now plus, because this would come in the form of reactant. So, this should be 2 into 236,964.2. This should be by 2 into 96500. This should become, if you do this calculation, then this value would become minus 0.8 it would become 0. Just a minute, let me find it out. 0.8 just hold on, let me find it out. It would become minus 0.827 volt. Now, let me put this value here. So, let me remove this part. Let me also remove this part. So, 0.827 minus sign. Now, OH minus can also be converted into H plus. It can be, this same thing can be written in terms of H plus ion concentration. How would we do it? Now, similarly for H2O, H plus OH minus, it can dissociate into H plus OH minus ion. For this reaction, we can also calculate what is equilibrium constant. K would be equal to, and if you have this situation, let us say in equilibrium and it is in neutral condition, then K would be equal to H plus concentration, OH minus concentration, H2O, and this is in pure H2O form. So, this should become 1. So, the K would be equal to this. Now, K is also related to del G0. So, K ln K would be equal to del G0 minus RT. Now, if you write in the form of log, so the same thing, you just change it to log and here you put 2.303. And now, if you put this del G0, which is nothing but mu of OH minus plus mu of H plus minus mu of H2O. There is a minus sign, RT into 2.303, and at 25 degrees Celsius, if you put all these values, you would get, which is close to 14.01 minus. So, now log is nothing but minus 14.01. Let me remove all this part now. So, this would be equal to 14.01 into 10 to the power minus 14.01. This should be 10 to the power minus 14.01, because we have seen log of K would be equal to, in the neutral condition, minus 10 to the minus 14.01, which you can write as 14. So, K would be equal to 10 to the power minus 14. So, I am just removing the decimal parts and then I am writing 10 to the minus 14. And again, for H2O, when it dissociates, it forms, if it forms one H plus ion, similarly it would also form one OH minus ion. So, number of H plus ion would be equal to number of OH minus ion. At the same time, the concentration of H plus ion would be equal to OH minus ion in the neutral condition. So then you can write it as H plus square equal to 10 to the power minus 14 in the neutral condition. So it becomes H plus ion concentration in the neutral condition would be 10 to the power minus 7. Now what would be the pH of neutral solution? So pH would be minus log of concentration of H plus would be equal to 7. So neutral condition, the pH of the solution or H2O water would be 7. Now from this relation we can write OH minus ion concentration in the form of OH minus ion concentration, let me minus equal to 10 to the power minus 14 by H plus. So I replace this OH minus concentration in the form of, replace this in this place. So if I replace this, we would get equal to minus 0.827 minus 0.059 log of 10 to the power minus 14 H plus. So this should become minus 0.827 minus plus 0.59 into log of 10 to the power minus 14 plus, so there would be minus sign because I have not taken this minus out, plus log of 0.059 log of H plus, there would be a minus sign, sorry, there would be a plus sign because this minus and here would be a minus sign, so that minus minus would become plus. Now if you take this, if you make it 0.827 plus, you will see that though we have taken 0.059, actually this value is coming from 2.303 RT by F, and if you put the values at 25 degrees Celsius, you would see that this is actually 0.0591. So if you multiply this to 14, because this 14 will come out, you will see that it becomes 827, and if you take minus out, then it would be minus 0.059 log of H plus, sorry, 0.059 into pH. So because minus log of H plus ion concentration is pH, so this becomes E ox rate would become 0 minus 0.059 pH. Now this is the equation for this relation, this reaction, and for this reaction also we have seen E equal to minus 0.059 pH. So the both the relations, final relation is same, both the relations are same. So that means practically these two lines, if you plot this line from this equation in the pH versus E versus pH diagram, as well as this reaction in the form of this, both should merge. So that means they should merge, and this line, this dotted line indicates the equation H plus plus E equal to H2, and this also indicate H2O plus 2E equal to H2 plus OH minus 2. But we have to see where we would get this relation, this reaction, where we would get this reaction, because this relation is pH as well as potential dependent. Now if you see this, here we have H plus ion. So, the reaction which involves H plus ion, that means it is happening in acidic medium. Now, this relation you see there is one OH minus, there are two OH minus ion. So, that means if the solution has excess OH minus ion, so that means that should be happening in basic medium. And also from the pH factor, if you see the 7 is the neutral solution, and the basic medium where we have excess OH minus ion, that should be pH should be greater than 7. So, this is basic, and less than 7 would be acidic, where you have excess H plus. That suggests that this reaction would happen in acidic medium, this reaction would happen in basic medium as well as in neutral solution, because up to neutral solution this reaction is possible, and from neutral to basic this reaction is possible. So, we can have a clear cut definition, and which is basically nothing but pH 7, pH equal to 7. So, the right side of this reaction would happen, left side of this reaction would happen. So, and what would be the value of the potential at pH 7? If it is pH 7, so instead of 10 to the power 14, here you just put 10 to the power minus 7. So, then you would see that this would become around 0.413. So, if we can have two reactions on the E versus pH diagram. Now, if you see this reaction, again you can understand that above this line H2O is stable, below this line H plus or OH minus both are stable. Now, that means this is stability line for H2, because so we have H2, and this beyond this above this line would be H2O stability region. Now, we have this reaction doesn't involve O2, this reaction doesn't involve O2, but we have come to know that there would be two other reactions which would be involving O2. Let us see those two reactions. So, one is same way, one would be happening in acidic media, because the reaction would be O2, which is dissolved oxygen, plus 4H plus 4E. This is also a reduction process going to 2H2O. Now, this same relation you can also write in the form of last equation, E0 plus RT 4F, because here we have 4 electron, ln O2, or now here we consider PO2, because this is in gaseous form, PO2 H plus ion concentration to the power 4, because there are 4 H plus ions. Now, H2O 2, this should be 1, this is the pure H2O medium. This, let us say this is considered to be 1 atmosphere, then the same relation we can write it as E0 minus, if you put all those values RT at 25 degrees Celsius as well as F and convert this ln to log, then you will say this becomes 0.059 pH, and this E0 would be around 1.223, 1.227 something, yes, 1.227, or it would be close to 1.23. This volt, much volt. This also you can find out from this relation, E0 equal to minus del G0 by NF, and here N is 4, and put the value of F and del G0, you find out from mu 0 of all those species, you would get this value. So, this is another relation, and at pH 0 this potential would be 1.227. So, here the potential would be 1.23 volt, and from that this straight line equation with a negative slope of 0.059 would start if the pH is 0, and it would also move like this, which would be parallel to this line. And here also this is acidic. So, this should again have a demarcation line which is pH 7, this is pH 7. So, below this pH we have this reaction, and again if you see below this H2O would be stable, beyond this O2 would be stable. And now we have one more reaction, that is O2 plus 2H2O plus 4E would be equal to 4OH minus ion. So, this is again just like H2O plus 2H2O plus 2E equal to H2 plus 2OH minus. Same way this relation, this reaction is also happening in basic or neutral medium, and this should start from pH 7, and the way I have done the calculations for this earlier two reaction, hydrogen ion reduction and H2O reduction, same way if you do this operation, you would see that for this, if you write the Nernst equation, you would get the same relation, 1.227 minus 0.059 pH. You would get the same relation. So, that means this reaction and this reaction, if you draw that reaction on the potential pH diagram, it would have the same line. Both the reaction would be falling on the same line with the same slope. So, beyond this pH 7, we will have this reaction. This reaction, below this we will have this reaction. So, now we see that this two from these four reactions which are involving H plus, O2 and H2O, we can pinpoint what is the stability zone for water, and that is called the water stability line or H2O stability region, and these are two water stability lines. So, now if you want to draw a Pourbaix diagram for Ni H2O system, then this should be my complete diagram. This should be my complete diagram with the reactions which are available in our hand. So, now we come to know the complete Pourbaix diagram for nickel H2O system. Now, from this you can see that if we are in this zone, let us say I am sitting in this portion with the potential of this much, let us say 0.8 volt and pH of 2. If I am sitting here, let us say within the solution, if I can maintain the potential at 0.0 volt and the nickel, if the nickel plate, that potential is maintained at minus 0.8 volt and the pH of the solution is 2, then the phase I would be getting at 25 degrees Celsius would be nickel. So, nickel will not go to nickel plus plus, that suggests that there would be no dissolution, and if there is no dissolution, that suggests that there is no corrosion, and here we are not having any corrosion and it is not forming any other species. So, then this zone we call it immunity zone. The boundary would be, let me fix the boundary would be, this is in this zone, this zone always will maintain nickel as nickel. So, that is called immune zone. Immune zone, or we call it immunity zone or immune zone. Now, if I am at this position, with this potential and this pH value, then we can see that Ni plus plus is the region. Now, the situation here was we have only nickel, no iron, but here we can see that there is a nickel ion concentration, nickel ion presence, and if the nickel ion presence is there and that nickel ion is actually forming from nickel that is dipped in the solution. So, we have the ion formation from nickel, and ion formation is nothing but the dissolution, and the dissolution means its corrosion. So, this zone we call it as corrosion zone. Corrosion zone. Now, the interesting part, now this zone would be this. So, this is my corrosion zone. Now, if I can go to this place, let me go to this place with the potential of this value and with the pH of this value, let us say pH is 9. Now, here the product is NiOH whole 2, or the zone, this place is in the NiOH whole 2, that is in that region. That means the product would be NiOH whole 2 from Ni or Ni plus plus. So, if you go from this region, so Ni plus plus will form NiOH whole 2. If I come here from here to there, or if I am here, if I go to this place, then I form NiOH whole 2. Now, NiOH whole 2, we have seen one problem, that if at certain pH value of the solution in deaerated H2O medium and with the solubility product of NiOH whole 2 at 25 degrees Celsius, we see that the nickel corrosion is not spontaneously possible. We have seen from thermodynamics. Now, this NiOH whole 2, it forms a layer on the Ni surface which prevents nickel dissolution. This region we will come to know when we come to know, we will come to know more about this later, but for the time being this zone is called passive zone, because though we have NiOH whole 2 which is the corrosion product, but it forms a layer on the surface of the nickel and prevents further corrosion. So, this zone is called passive zone. So, that means we have immune zone, corrosion zone and passive zone. So, this information what we are getting, which zone would be immune, which zone would be corrosion and which zone would be passive, this would be a very, very essential information we need to have, and this will guide me whether thermodynamically whether nickel is able to corrode in the solution or not. That information we would get from this. We will come to the advantage of Pourbaix's diagram, but let me also give you some other example. For example, in case of aluminium, let me just put the equation, and then finally this should be a sort of exercise. If you do the calculation the way the calculations for Ni system is done, you would also get a Pourbaix's diagram for Al2O aluminium H2O system, and finally you would get the Pourbaix's diagram for this also. The reactions would be, one is Al plus 3 plus 3E going to Al. This is equation number 1. Equation number 2 would be 2Al plus 3 plus 3H2O going to Al2O3 plus 6H plus 3 2Al plus 3H2O going to Al2O3 plus 6H plus 6C. Similarly 4 you can also write Al plus 2H2O equal to Al O2 minus plus 4H plus 4 plus 3, and the way equations are written just to maintain the overall charge balance. Another reaction that is possible, which is Al2O3 plus H2O equal to 2Al O2 minus plus 2H plus, and the values of mu 0 Al plus 3 would be equal to minus 839,800 joule per mole, mu 0 Al2O3 would be equal to 160,8900 joule per mole. Like that you can similarly we can also have the mu 0 of AlO2 minus this data sorry, I made a mistake. This value would be 481,200 and this is 839 minus 800 joule per mole, and all the other values you know already, because H2O you know, H plus, all other values are known. So, if you do the same operation, then you also get a Pourbaix diagram for aluminum system, and here the interesting part is this ion, because there in nickel system we have Ni plus plus ion only with the information what we had, but here you have two ions, Al plus 3 as well as AlO2 minus, and whenever we have a metallic ion, whether it is a complex ion or a simple ion, but if the metallic ion is going in the solution, then always it would be a sort of dissolution. So, this ion, if it forms from Al, for example number 4, if this ion forms from Al aluminium, then of course the aluminium is corroding. So, we have to see these relations. Again, if you see these relations, this is potential dependent only, because we do not have any H plus ion involvement. Here we have H plus ion involvement, but it is not an electrochemical reaction. So, this reaction cannot be expressed in the form of Nernst equation. So, this will be pH dependent but potential independent. Now, if you come to this, here we have H plus as well as electron involvement. So, this should be potential as well as pH. So, this is, let me write this potential dependent, this is pH dependent, this is potential E as well as pH. Same way this should also be E as well as pH, because we have H plus ion as well as electron. So, E and pH, and this is again you see only H plus, no electron. So, this is also only pH dependent. So, if you know this too, pH dependent, that means it always should be a line which is vertical to the potential axis. Okay. And if you have potential pH as well as potential, that would always be a line with a slope in the E versus pH diagram. Now, that we have to see whether the slope is positive or negative from this Nernst equation. So, you see these 5 reactions, you can also put it in on E versus pH diagram, and let me remove the nickel part. Let me put these reactions in a E versus pH diagram. Here I will not put any values, this would be a kind of exercise. So, if you do it, so it would be very clear how to plot, how to draw a Pourbaix diagram for a metallic system, and if you know all those reactions which involve H2O. Now, in this definitely this should be again a line which should be parallel to pH axis, because this is P potential dependent, pH independent. This would be a line which is parallel to this. Now, initially I will draw all the lines dotted. Let me draw it dotted, because then we will connect it. So, this is dotted line which is giving the reaction number 1, which will be a line parallel to pH axis. And at 0 potential, 0 pH value, this should be the value of the standard reduction potential if the activity of Al plus 3 is 1, or the concentration of Al plus 3 would be 1. Now, let me see the pH dependent reactions. Those would be a simply vertical line and parallel to this voltage axis or the potential axis. So, this is potential. So, this should be one reaction would be this, reaction would be this, the other reaction would be this. Now, if you find out the values of K or the equilibrium constant for this reaction as well as this reaction, you would see that this would be the reaction number 2 and the reaction number 3 would be, reaction number 5 would be placed somewhere here, and you have to find out what would be the pH value from equilibrium constant. From equilibrium constant you can find out what would be the, at what pH value this should start, this vertical line would start, and if the activities of those ionic species are 1 or the concentration of the ionic species are 1. This should be equation number 2 and this should be equation number 5. Now, let me put the regions, let me demarcate all those regions, let me put all those species on this. So, definitely below this line would be aluminum, above this line would be Al plus 3. Similarly, left side of this, for this reaction, if you see the left side of this would be Al plus 3 and right side would be Al2O3. And now, if you see this reaction, the left side of this would be Al2O3 and right side would be AlO2 minus. So, throughout this section I can have this, throughout this section I can have Al plus 2. So, it is a mixed thing, but once we draw these vertical lines, we can clearly see that left side of this would always be Al plus 3, right side would be Al2O3 and right side of this line would be Al minus 2 minus 1, AlO2 minus. So, we can segregate, we can put all those spaces and we can specify the regions. Now, still we are not sure whether up to what extent this can remain below this line or up to what extent this can remain below this line. So, that would be decided by this potential pH diagram, potential pH reaction at these two reactions 3 and 4. If you see this, then find out what would be the final relation in the form of E and pH, then you will say this would be having a negative slope, and that negative slope you have to find out with the help of Nernst equation. So, this should be a line which would be going like this. Which would be going like this, and this line and this line will merge at this point. If you take unit activity of different species, and let us say if you are taking aluminum plus 3 activity to be 1, then you have to take all the activities of ions as 1, and if you take it 10 to the minus 2, then this is one ionic species, this is one ionic species. If it is 10 to the minus 2, you also take it as, take this concentration of ionic species to be 10 to the minus 2, and this would always be 1 because this is a oxide phase which is settling down and which is not dissolving in the solution, and this would also be 1 because this is a pure metal. Now, this line indicates the equilibrium between aluminum and Al2O3 if you consider the species which are formed by aluminum. Now, again you can see that below that slope line would be aluminum, because we already know that this region would be aluminum, and beyond this line would be Al2O3. Now, if you see that this zone below, above this line would be Al plus 3. So, that means there must be, if we have this line, let us say we have this line. So, there must be some reaction which involve Al plus 3 and Al plus 3 and Al2O3, because above this line would be Al2O3. But since we have already Al plus 3, so this line will have a virtual presence, but actually it will not be present, because which is a demarcation line between Al plus 3 and Al2O3. So, left to that line there will not be any Al2O3, and at the same time this line indicates the equilibrium between Al and Al2O3. So, this line will have a virtual presence, but actually it will not be present in the diagram. So, if it is actually not present in the diagram, so we will just put this dotted part here. Now, we know that this line we can make it a solid line, just to indicate that below this line would always be aluminum, beyond this line would be, above this line would be Al plus 3. So, now we know what is one solid line, which indicates that actually that line is present. Now, similarly we can also have this relation, which again let me take it little down, this axis. Now, again this is the equilibrium between Al and AlO2 minus. So, that means it should start, this line should start from this point, because beyond this line or right side of this line we will have that existence of AlO2 minus. So, left to that line, this equation will not happen. So, again I can see that this is again having a slope which is negative. Okay, this is basically for equation number 3, and this is equation number 4. So, this 4 is basically equilibrium between aluminum and AlO2 minus. Now, we have, and this line will have a virtual presence, but actually it will not be present in the diagram. That means that this will not be a solid line, because this is going into Al2O3, which is not the part of this reaction. So, now we can specify another region, which is this. We can draw a solid line. This is a solid line. Now, similarly this relation we can also have a solid line, because this would be a boundary between aluminum and AlO2 minus. So, again equation number 4 would be a solid line, and you will see that this line and this line all will intersect at this point. If you take the same activity, okay. Now we see that above this line, above this point, let us say this line Al2O3, above this line left side of this point would be Al plus 3. So, again we can have a solid line which will demarcate the region between Al plus 3 and Al2O3, then this would be another straight line, another solid line. Similarly, this would also be a solid line. So, now after doing that we will remove all those dotted lines. All those dotted lines. Now, this should be my Pourbaix diagram for aluminum H2O system. Now, we will also have all those 4 reactions which involve H plus, O2 and H2O, and that would be again the same thing, 2 line which are plotted in the Pourbaix diagram in the form of dotted line, and this 2 line, that means this is basically O2 reaction. I am just writing O2 reactions. In one case it would be O2 plus 4H plus 4E going to 2H2O, which is happening in acidic medium. The another reaction which is O2 plus H2O plus 4E going to 4OH minus, that is happening in neutral or basic medium. So, beyond this line it would be O2 region, O2 stability line. Below this line it would be H2O stability region, below this is H2 stability region. So, again we have the stability diagram for water. Now, here the interesting part, in case of nickel we have seen that nickel, let me draw the nickel Pourbaix diagram in this, it would be like this. I am not drawing that H2O regions. Now, here this is Ni plus 2, NiOH whole 2. Now, that case this is my immunity zone, this is my corrosion zone because ion is forming, and this is my passive zone because we have NiOH whole 2 formation on the nickel surface and it passivates the metal. But here you see similar way, this is immunity zone, and this is corrosion zone because we have ion formation. Now, Al2O3 it forms a layer on the surface of aluminum and passivates the metal. So, this would be a passive zone. Now, here interestingly this region again we are forming an ion which is of course a complex ion, but whenever ion is forming that means it has some dissolution ability in the solution or in H2O. So, if AlO2 minus ion is forming, it also suggests that it is a corrosion, because from aluminum we are forming an ion and aluminum is corroding in the form of AlO2 minus. So, this is again a corrosion zone. So, here we have immunity zone, corrosion zone and passive zone, but generally we see that if the pH is increased, okay, if you increase the pH we see that gradually the tendency to become passive is increasing, because we have the tendency to form this layer on the metal surface is increasing. But you can experience in the same way in case of aluminum, you see if you just let us say this is my potential I am maintaining, this is my potential axis, this is my potential values where I am at. I can maintain the potential of aluminum rod which is dipped in H2O at this value. Now gradually I increase the pH value of the system, of the solution. Now you see, as we increase the pH, if I am at here, at this position, I have immunity. You see that pH, if this is my pH 7 which is the neutral solution, we have common understanding that if the acidity increases we have more corrosion, but that does not happen in this case, because even if you have a very highly acidic medium, but if your potential is below certain level, then you can have no corrosion. The similar way, we have that common intention that if we increase the pH, let us say I am going to this place which is the pH is let us say 8, when we have a basic medium we always experience OH metal hydroxide formation or metal oxide formation, like just like this. Then we can say that this material is going to passivate in that medium if the pH is more than 7 or if it is basic medium. It's of course it's true, okay, up to this, in this case up to this it is true. So this zone we can always have a passive zone, and even if and the pH gradually increase in pH, it improves the passivity level. But once we cross this passive zone, this line, if we go to the right side of this line, and that case the pH is a very high value, and this would become at around 14. If you calculate all the K values or equilibrium constant, and then you will see that this is coming at around 14, pH value of 14. So you will see that even the pH level goes to a very highly basic, still we can have, instead of passive layer we can have a complex ion formation. So if we have a complex ion formation, that also suggests the corrosion. So it is also not true always that if you have a higher pH value you can have a lower corrosion or you can have a passive zone. You can also experience corrosion zone if at higher pH value you form a complex ion. So depending on what are the ions that you experience in a particular system, aluminum H2O system, this is the case. In case of nickel system, you will always have, even if you increase the pH value, you will have also have this region, entire zone is passive zone, you can always have passivity, but in case of aluminum you can experience corrosion if you have a complex ion formation at higher pH value. So you have to judge a Pourbaix diagram for a system carefully and see at what pH value and what potential value you can go to a passive zone. I will come to that part why we need to go to passive zone, because it is very difficult to maintain at this position, rather it is very easy to go this region. We will see later on, but for the time being this is my entire, this is basically the way we draw a Pourbaix diagram from thermodynamic data, and it is pretty clear that this pH versus E versus pH diagram, it considers only the thermodynamic data. It gives you the possibility of a different phase at different potential and pH value, but it cannot specifically say that what would be the rate of the reaction, because this does not involve any kinetics. This is to be taken in mind, but because this is a thermodynamic diagram, not it does not give you any practical rate equation, rate values. Fine, thank you.